Engineers often view algorithmic patterns like monotonic stacks or 1D dynamic programming as artificial hurdles designed for the interview room. There is a common perception that these abstract challenges have little bearing on the day-to-day reality of writing production code. This buckling server rack illustrates the scale of a digital collapse. In production, an inefficient log analysis loop consumes every available CPU cycle, effectively paralyzing the pipeline under the weight of its own data. The constraints of the coding interview, big O scaling, space complexity, and concurrency, are the same constraints that govern distributed system design. To navigate these constraints, engineers use the PACER framework: problem, analyze, construct, execute, and review. This methodology maps abstract coding templates directly to the architecture of high-scale systems. Algorithmic templates provide the logic required to build high-throughput, fault-tolerant infrastructure. In a typical technical interview, the challenge of tracking state over time is framed as a time-based key-value store. The goal is to retrieve the value associated with a specific key at a specific timestamp. A standard hash map fails this requirement because it is designed for O of 1 exact match lookups. A hash map is an unordered data structure that maps keys to values, making it incapable of retrieving the closest previous timestamp without checking every entry. The algorithmic solution maps each key to an array of values that is strictly sorted by timestamp. This structure ensures that as new data arrives, it is appended in a predictable order. This pattern appears in production when calculating rolling averages for CI/CD build performance. To avoid the overhead of querying a massive relational database for every request, the metrics must be stored in memory for rapid retrieval. A linear scan of this metrics array takes O of n time, making real-time monitoring impossible at scale. Applying a binary search algorithm eliminates this bottleneck. By repeatedly halving the search space, the system locates any timestamp in roughly 20 steps. Using the lower bound and upper bound variants of the search allows the system to isolate specific time ranges instantly. Lower bound finds the first element not less than a value, while upper bound finds the first element greater than it. This reduces the latency of metric extraction from O of n to O of log n. Optimization at the data structure level is the primary mechanism for preventing performance degradation at the application level. Identifying the most frequent failure states from millions of real-time logs is a core requirement for system observability, isolating the top error patterns immediately. This is the production equivalent of finding the top k frequent elements in a dataset. Comparison-based sorting algorithms scale at O of n log n, which introduces a lag between an error occurring and an alert firing. For high-volume log analysis, we need a solution that approaches O of n, or linear time. Bucket sort achieves this. Instead of comparing elements to each other, we use an array where the index itself represents the frequency of an item. We can implement this logic within an error analyzer class designed for real-time log ingestion. The analyzer normalizes logs to group similar errors, storing patterns in a hash map. It increments a counter upon detection, then maps counts into a bucket sort array. Errors with 50 occurrences move to index 50, achieving perfect ordering without a traditional sort. The top k errors are extracted by iterating through the bucket array from the highest index downward. Achieving O(n) time complexity ensures automated alerting systems fire without lag, turning a theoretical optimization into a requirement for system reliability. These algorithmic constraints become even more rigid when data structures span multiple nodes across a network. Distributed systems are governed by the CAP theorem, meaning networked systems must choose between the guarantee of strict consistency, the promise of continuous availability, and robust partition tolerance. In practice, engineers must manage the risk of stale data during network failures. The solution is log-based change data capture, or CDC. CDC reads the database's internal transaction log to replicate changes in real time. Traditional batch extraction fails at high scale because it relies on concurrency locks. These locks prevent the database from processing new transactions while the data is being copied, causing the source system to stall. This pipeline is a large-scale implementation of the producer-consumer problem, a classic concurrency challenge involving shared buffers and thread synchronization. The producer is the log reader, extracting change events as a continuous stream of data blocks. These blocks flow into a distributed message queue, like Apache Kafka, acting as a bounded queue. Finally, the consumer destination connector writes data into the target warehouse. In a distributed system, network partitions make it impossible to guarantee that a message is sent only once. Duplicate deliveries are a certainty. To maintain data integrity, the pipeline must ensure exactly once delivery semantics. Each record must appear in the warehouse exactly as it appeared in the source, with no duplicates or omissions. The system achieves this through idempotent operations, specifically upserts tied to unique IDs. An upsert inserts a new record or updates an existing one, ensuring that duplicate messages do not result in duplicate data. This idempotency logic is the same state tracking pattern used to prevent infinite loops in graph traversals. By checking the current state before applying a change, the system maintains consistency regardless of how many times an operation is repeated. A distributed data pipeline is essentially a localized data structure scaled across a network, governed by the same concurrency and space-time rules as a whiteboard interview. From local pointers to distributed queues, the progression of modern engineering is defined by the efficient management of data. We have established how binary search optimizes CI/CD metrics, how bucket sort enables real-time log analysis, and how the producer-consumer pattern powers CDC pipelines. The rigor of algorithmic analysis, tracking amortized complexity and avoiding memory leaks, is the foundation of scalable engineering. The logic used to prevent a concurrent modification exception in an array is the same logic required to prevent deadlocks in a global database. Whether passing an interview or architecting a pipeline, the underlying physics of data remain the same. Master the algorithmic templates, and the architecture will follow.